Hello everyone, this is Professor Ma. This is the short lectures on limits, part one. Okay. Now we're going to talk about very important ideas or notations and concepts in calculus, you know, the concept of limits. Recall last time where we left out, we tried to calculate the derivative, the tangent, or the slope of the tangent line. Okay, and the way we did it is we take if we wish to calculate the slope of this red line, instead we move the point a little bit by the amount of h, some small minute amount, and we go to the neighbors of x and go to x plus h. Then we connect this black line, which we can calculate the slope readily because I know the equations of the green line that they sit on. And I can clean the algebra up and I say, oh, okay, the slope I will get depends, of course, depends on where x is. It depends on how big h is. And I get this formula for the slope of the chord. But I don't want the slope of the chord. I want the slope of the red line. So of course, what I do, the next step is I'm going to take the h and make it smaller and smaller. In other words, I'm moving my neighbor, the point over here. I'm going to talk about this line that actually connect the neighbors, the neighbor that's closer and closer to the point x. In other words, in the algebra, in this formula, meaning we're going to let h become smaller and smaller. So as it goes on, then the h becomes smaller and smaller. Then the black line then begin to link into the tangent line. In fact, that's what we define the slope of the tangent line to be. Is what happens when h becomes zero in this formula. Shrinks to zero. Attention, shrinks to zero. Okay, my face shrinks. But, okay, and then this is the point we want to introduce the notion of limit. We want to make these ideas of shrinking to something or something approach something in terms of limits. Okay, so the first things we would like to do, I would like to do is to clarify what do we mean when we approach, say, zero from the right-hand side. And there are a couple of versions of these you can do. There's a continuous version and the discrete version. I'm doing the discrete versions, okay? And the for continuous versions, you can check the epsilon delta versions. Lot of textbooks has that. So this is discrete versions of what we mean when we say the x approach zero from the right-hand side of x. Okay. So to clarify that, first we say what we mean by having a sequence approaching a particular sequence. That means a list of numbers, and this list of numbers is getting closer and closer to zero, but they all stay to the right-hand side of zero. In other words, in pictures, this is what I'm thinking about, a bunch of dots that become closer and closer to zero, but they all stay on the right-hand side. That's what a plus sign is for, meaning, oh, it's on the positive side. Two sides, the left-hand side is the negative side, and the right-hand side is the positive side, okay? And what we meant by that is actually the following meaning, to make it more precise. What we mean by that is if it's for any number, positive number I can think of, okay? And I look under the microscope and I blow this up and very close, and I put down the little neighborhood of epsilon, okay? We say x, a sequence goes to zero from the right-hand side if it's regardless how small this neighborhood is. Basically, only finally of the numbers that are in the sequence, in the list, in the set up there can be only finally of them that's outside of this little stretch. It doesn't matter how small the stretch is. This is another way to say the following. It doesn't matter how small these little intervals, okay, space there is, most of my x's are in that space. Only a few that are kind of outside. This is one conceptual definition of what we mean by a sequence of numbers going to 0 on the positive side, the right-hand side, 0 plus. Okay. And using these, we're going to say, okay, suppose we understand, say, what we means to say in general, x go to 0 from the right-hand side, x is a variable. Basically, what it means, it doesn't matter which sequence that's going to the 0 from the right-hand side in this discrete version. It doesn't matter what sequence you can think of that goes to 0 plus, okay, you get obtain the following results. So for example, what I meant by that is we clarify what we mean by as x go to 0 plus. That means for every sequence you can think of that's going to 0 from the right-hand side, and you plug it into the formula x plus 2, and the obtaining outputs is going to get closer and closer to 2, which is exactly what you expected. This, as x becomes smaller and smaller, then x plus 2 gets closer and closer to 2. Okay, and so we'll write these in the following limit. Okay, so we'll say when the variable x goes to 0 from the right-hand side, becomes closer and closer to 0, then the formula x plus 2, the output, the limit, its limit is equal to 2. Okay. And from these, then we can define what we mean for x coming to the 0 from the left-hand side. So you can, so this is the formulations of exactly the same thing we have, except this is limit approach, x approach 0 with a little minus sign in the exponents. That means x stays to the left-hand side of 0. So if I choose a bunch of number that's negative, that's what it means to be on the left-hand side 0, but they're getting closer and closer to zeros. Okay, and then I plug those numbers into x plus 2, and the output again will be closer and closer to 2. Okay, the output will be smaller than 2, slightly smaller because x is negative, but they will be just below 2, but they're getting closer and closer to up to 2. And we will write this as the following limit, as the limit goes to 0 from the left-hand side, the formula output x plus 2, it will stationarily approach the number 2. Okay. And then this finally what we mean when x approach 0, meaning it doesn't matter right-hand side or left-hand side. And then this in picture, it means the numbers of the sequence of numbers, it doesn't matter how small of a little stretch of a neighborhood around 0 I make. Doesn't matter how small it is, most of the number x that in the sequence has to be in this neighborhood. Only finitely can be outside. If such is the case, then this sequence is going to 0. That this is what we meant by going to 0. In other words, I can think of a list of numbers like, for instance, 1/2 minus 1/3, 1/4 minus 1/5, and so on and so on. And so I'll be thinking a bunch of numbers going back and forth, but as I go on and the number becomes closer and closer to 0, they bounce around, but the only finality of this list of numbers is outside of this neighborhood. It doesn't matter how small of this neighborhood is, it's only finality of these numbers fractions is outside of it. Okay, so this is what basically we meant by us the variable or sequence approach, the limit, the sequence of number approach a certain limit x approach a. Okay, then of course when we say x approach 0, and then we get the following result, means doesn't matter what sequence you can think of. Okay, it goes to 0, and you plug in those sequences into the formula, and then you will get exactly the same result every time. Then that result L is called the limit. So for example, here we are talking about when x becomes smaller and smaller. It doesn't matter. It goes to 0. That means you're allowed to. You should think of x could be positive, x could be negative, and because sometimes there is being positive or negative has a drastic difference when you plug into the formula. Okay, in this one it doesn't matter. So in this case, I'm thinking of suppose x is a very small number, and I plug into this formula, and what would the quotients becomes? Well, and we can analyze these in two separate steps. First, when x become smaller and smaller, becomes 0, the top becomes closer to the numerator 1. And the bottom, when we plug in 0 becomes smaller and smaller, x becomes smaller and smaller. 2 times x becomes smaller, becomes 0. So the bottom goes to -1. Therefore, the quotient goes to 1 divided by -1. The answer is -1. Okay. So, if you try this with a calculator, plugging a bunch of numbers where it goes into from very, very small and put into this formula, you will find the output becomes closer and closer to -1. And that's the limit. Okay. And we say the same things. Basically, if we change the number 0 in the picture to any center at any number a, we can talk about x goes to a from the positive side, x goes to a from the negative side, x goes to a from both sides, or limit x goes to a. And we say limit x, f of x is L as x goes to a, or simply as xi goes to a, we say f of xi goes to L for every sequence you can think of that goes to the number a. You plug it in, you will get the same result L. Okay, so what are some of the rules for limit? Here are some of the basic rules, and if I know what the limit when x approaches a number a, I know the result for f of x. I know the result that will come out to be some limit for g of x, and then I can calculate the individual result and add them. And similarly, if I multiply two parts and I know the result of the limit of each one, then the limit of the product, I can multiply the result of the limit of individual ones. Same thing for quotients, as long as the denominator doesn't go to 0. Okay. They have some basic limits. Constant never change, so there's no x. So x goes to any number a, the limits, constant limit c. The formula x, when x becomes closer and closer to a, the limit for the number x is a. Okay, so limit x becomes closer and closer to 5, then x becomes closer and closer to 5. The limit is 5. If I multiply a x by a constant, and then as x gets closer and closer to the number a, then the result will be just that constant c multiplied to the limit. In other words, constant can be pulled out. I can calculate the limit and then multiply the result by the constant. Like here, I mean, the 3, I can think of this. Oh, I don't have to worry about 3 first. Let me calculate what's the limit of 5, and that's 5. 3 times 5 is 15, so it's 15. That's the line of reason, right? Same thing with power. Okay, when x approach the number a, and if it makes sense to take a to the power p, then the end result will be just a to the power p. So for example, if x gets closer and closer to 25, then square root of x, it gets closer and closer to 5. And so these are we taken for granted. Okay. What about limits for polynomial and the rational formula? In general, if in elementary functions, if the function is defined at a point x equal to a, okay, and there's with a little neighborhood around it, actually, besides at precisely actually a little bit piece around x to a, and then the limit you can always just plug it in. Okay. In this case, in polynomial and rational formula, basically says, oh, you can just plug in the numbers. It's exactly what you expect that to be. Okay. So for example, here's a rational formula, okay, and x become closer to 1. All you have to do is plug in the 1, so top is 3, the bottom is minus 2, so the answer is minus 3/2. The quotient become closer to minus 3/2. Okay. And this is in general true for elementary functions. And the things you have to be careful is sometimes the question doesn't make sense. For instance, we can say when x approaches 0 from the right-hand side of square root of x, I'm taking positive number of small number, then the answer will be get closer and closer to 0. So I can say the limit of x coming from the right, okay, is 0. But you cannot say as x coming from the left, you get 0 because it's not defined. Nor can we say x coming, the limit of x goes to 0. Okay, it has to be specified 0 plus. Then this sentence, this result, the limit 0 stands. You are not allowed to use negative number. So these are things we think about when we talk about limits at the boundary. Okay, from the right, from the left. The notion of infinity. Okay. But what do we mean by infinity? Well, let's talk about what we mean by a set is bounded and not bounded. Okay. I have a bunch of numbers. We say the bunch of numbers bounded above is they are all smaller than some numbers on the right hand side. No, there's some limits. There's some cap on this list of numbers. Okay, here I use a capital R to say, oh, on the right hand side there's a limit. Every number in the list is smaller or equal to this number, then we will say this set is bounded from above. Similarly, what we mean by bounded from below is that there is a number that's the floor of all these numbers that's in the list. That everything in the list is bigger than or equal to something on the left-hand side, a floor, L, on the left. Of course, it has to be on the left of everybody, right? And this is a set bounded from the left. And we say a set is bounded, period, meaning it's bounded both right on the right and on the left. Okay. So a set is bounded if it's within an interval, finite interval, if you like. Okay. And why is this important? Well, notice this limit, the f of x equal to 1 over x. Okay, and if we plug in as x goes to 0 on the right hand side, we get a list of output that's not bounded, because from the right hand side it's bounded from the left, but not bounded from the right. And this, and yes, gets bigger and bigger, and this goes, we say these sets goes to infinity. And when we say a sequence of number goes to positive infinity, okay, and it means is zero, and there's a bunch of numbers, they become bigger and bigger. We say they go to positive infinity if for every interval you can think of, it doesn't matter how big this number you can think of. There's only finitely many in here. Most of the number has to be outside. If a sequence satisfies these conditions, doesn't matter how big of a number you can think of, just about everybody's outside that big number we can think of, then this sequence, we say it's going to positive infinity. Okay? And in particular, if x go to 0 plus, then then the output will go to positive infinity, become bigger and bigger. If x goes to 0 minus on the left hand side, because the output fraction is negative, then you will get bigger and bigger negative numbers. Okay, and so we write equal to infinity doesn't mean this infinity is a number. This is very, very important. What it meant when we say this is equal to infinity, it means that these limits begin to increase without bound. It becomes bigger and bigger as x gets closer and closer to 0. Okay, so I know in other words, I know the behavior of the output. Same thing here. I know the behavior of the output becomes more and more negative without bound below. It's negative than many numbers one can think of. Okay? You will pass that point. But limit as x approaches 0 is not defined, because I don't know in limit x approaches 0 in this case, I don't know what a sign of 1 over x is. It could be very large if x is positive and close to 0. But if x is negative close to 0, then the number fraction will be very negative. So I don't know the behavior. It's kind of erratic. It depends on x being negative or positive. The quotient can be quite different. It's different from the above two cases. So in this case, we say the limit is truly undefined. Okay, or chaotically, and it's chaotic. Okay, it's undefined. But the ones on top, even though there's no limit, I cannot tell you what the limit is because there isn't. But I know the behavior goes positive, negative, infinity. Okay, and that's why sometimes we see square absolute value around the formulas in these limit problems, because we want to kind of eliminate the positive and negative dilemmas, and to make the computation a little bit more clear for the examples. Okay. And then we say x goes to infinity, something happen. If you plug in the number become bigger and bigger, then the output becomes more and more close to L. Okay. So for example, when x becomes bigger and bigger, 1 over x becomes smaller and smaller, becomes 0. Okay, even though I know it's 0 plus. Okay, if I goes from the left-hand side, x become more and more negative, then 1 over x becomes smaller and smaller. So they both go to 0 from different side. Okay, of course. In this case, we see the limit of x. Excuse me. Oh, sorry. There's two other cases that I want to demonstrate. That so we have this with x from the before. We have x go to 0 from the right-hand side. 1 over x goes to infinity, and if x goes to 0 from the left-hand side, and then the output 1 over x goes to negative infinity. So this reflects on the graph on the vertical asymptote. One goes up, one goes down. Right. And in terms of x going to infinity, then we have when x goes to infinity, then 1 over x goes to 0. That's y becomes very small, but it's positive, so it stays on top. then 1 over x, if x goes to negative infinity, it's very close to 0, but it stays below 0 because it's negative. Okay. And that's from the horizontal asymptote. Okay. Finally, let's address these things about infinity a little bit. The infinity is not a number. It's a concept that basically says that the process will become bigger and bigger without stopping. There's no cap on it. It just blow up without any boundary. Okay. If this is descriptions, then we can talk about the following quote unquote of arithmetics. Okay, so for example, when we say go to positive infinity, then we usually think of 1, 2, 3, 4, goes to positive infinity. And goes to negative infinity, we'll think of -1, -2, -3, more and more negative numbers. Okay, so here are some rules which is true. Infinity plus infinity is equal to infinity. If I know the calculation of one answer become bigger and bigger, and calculation of another one become bigger and bigger, they both go to infinity, then adding them, the finished formulas go to infinity too. Okay, so x goes to infinity, x squared goes to infinity, so x plus x squared, we all go to infinity. The same thing for multiplications. When x goes to infinity, past infinity, x squared go to past infinity, multiplying them, okay, I'll get a product to be going to past infinity. Okay. If I multiply the constant to a formula that goes to infinity, and then the finished product is true, still goes to infinity. So if I multiply the formula that goes to infinity multiplied by 3, it still goes to infinity. If I divide a constant by something goes to infinity, then the quotient becomes very small, go to 0. Okay. And then finally we have raising power. That's kind of interesting. And that separates numbers into 2 types. And the numbers, if I pick a number between 0 and 1 and I keep raising power, then the number will go to 0. Become smaller and smaller. But if I were to take a number from here, I'll raise power b. This b here will be b squared, and the bq will be here, and they will go to infinity. Okay. So this is an interesting behavior, and here's b squared, and so on, so on. And so this is examples of them. Okay. Now, we cannot say anything about these. Okay? If I have a formula goes to infinity, another formula goes to infinity, I subtract them, I don't know the behavior of the difference. So for example, here are 2 formulas, they both go to infinity, but if I subtract x minus x, in this case I get a formula, its limit 0. Because x minus x is 0. But if I subtract x squared minus x, it's infinity minus infinity. In this case, because x squared will be bigger than x, and they will go to infinity. In other words, just knowing this and that, I don't know the behavior of subtracting them. Okay? So this is inconclusive. Meaning what? Meaning if I plug it in, and meaning there are more works to do. Okay? When we fall into this, and when we get into this form. Okay. Same thing with the fractions. If I have a fraction with a numerator become bigger and bigger in the limit, in the denominator become bigger and bigger, there's no conclusion about what the entire ratios of the fraction limit is going to be. For example, x goes to infinity, x squared goes to infinity. If I look at x divided by x squared, that's 1 over x. Okay, when x goes to infinity, maybe most x dash goes to infinity. Okay, x divided by x squared is 1 over x. And so 1 over x, 1 divided by infinity is 0. Okay? But if I were to take that fractions turn around, x squared over x, this is the formula just x, of course. So this is going to the same thing as x. So in this case, the ends of infinity. So in other words, in both cases, okay, x divided by x squared or x squared divided by x. I'm looking at infinity divided by infinity, but from there, I don't really know which case it is. So there's no conclusion we can draw if I wind up with this format. So meaning what? Meaning again, it's like the case right above. We're going to do more algebra to figure out the limit. Okay, later on we will have some of these examples. Okay, we call this inconclusive form. Okay. So for example, if I say x goes to infinity, and I say what's the limit of the formula 3x plus 4 divided by 5 plus 6? Well, if I plug in the formula infinity divided by infinity, so I don't know what I couldn't tell. So we'll have to do something else. And in this case, it will be 3/5 the limit. Okay. If you think of x become bigger and bigger, and it turns out as x become bigger and bigger, remember this portion becomes so large, the 4 and the 6 is really irrelevant. And then the ratios get closer and closer to 3/5. And if you don't believe in it, plugging a large number into these fractions, that's what you get. Okay, so this is the first part of limit, or basically definitions. Yeah, that's it. Have a good day. Bye-bye.